All right, let's get into it. Today, we're not just going to be in the lab. We're going to be detectives. We've got a classic chemical mystery on our hands, and our mission is to solve it.
So picture this. Someone hands you a little vial of some white powder. No label, nothing. It could be almost anything. And your challenge is to figure out exactly what it is using just your brain and a few key chemicals.
You see, this whole challenge is the core of something called salt analysis. And trust me, it's way more like solving a puzzle than it is just following a boring lab manual. It's all about deduction.
Now, every salt, and I mean every salt, is made of two parts. Think of them as our two main suspects. We've got the cation, which is positively charged, and the anion, which is negatively charged. Our job? Find them both. You do that, and boom, case cracked.
Okay, so let's break down our targets. The cation is also called the basic radical, because it comes from a base. The anion, that's the acidic radical, since it comes from an acid. And here's the key rule for our investigation. We always go after the anion first.
All right, detective, let's get this investigation started. First order of business is to identify that acidic radical, the anion. And the way we do that is with a series of what I like to call interrogations. Our first interrogation is, the gentle approach. We take just a tiny pinch of our mystery salt, add a little bit of dilute sulfuric acid, and then we just watch. We're looking for any kind of reaction at all, but especially for any gas that might bubble up. This one simple step can give us a huge lead.
And these are the clues we're hunting for. If you see a ton of bubbles, like a soda you just opened, that's screaming carbonate. Get a whiff of vinegar? Yep, that's acetate. And that, well, that unmistakable rotten egg smell? You found sulfide. But here's the thing, and this is super important. If nothing happens, that's still a massive clue. It just tells us our suspect is a bit tougher to crack, and we need to bring in more serious methods.
So, what if that first interrogation gives us nothing? No bubbles, no funky smells, just silence. Well, that just means our anion is playing hard to get. It's time to stop being nice and bring out the heavy hitter, concentrated acid.
For this next phase, we grab a fresh pinch of salt and, being really careful here, add some concentrated sulfuric acid. Sometimes you even got to warm it up a little bit to encourage our suspect to talk. And just like before, we're watching closely for any gases.
And the clues we get here are way more dramatic. A sharp, pungent gas that kind of stings your nose, that's probably chloride. You see a reddish-brown gas filling up the tube? You're looking at either bromide or nitrate. But if you see these incredible, beautiful violet vapors, oh yeah, that's iodide for sure. And if you still get no reaction, that narrows it down even more, pointing us towards suspects like sulfate.
Okay, so we've got a pretty good idea of who our anion is. Now it's time to switch gears. We're going after our second target, the cation, aka the basic radical.
Now, the hunt for the cation is a totally different ballgame. It's not about one-off tests. It's more like a systematic raid on a series of known hideouts. See, cations are organized into groups, from group 0 up to group 6, and you have to check each hideout in order, one by one. This chart right here, this is our roadmap. You can't skip ahead. You start at the top with group 0, testing for ammonia. If that's a bust, you take a fresh solution of the salt and test for group 1. Nothing? Okay. Now using that exact same solution, you move on to test for group 2, and so on. You only move to the next hideout when you've confirmed the current one is empty.
And hey, let me give you a little pro tip, a real veteran detective's trick. One of your best tools, just your eyes. If that powder you started with was white, you can immediately rule out suspects like copper. Why? Because copper salts are pretty much always a vibrant blue. A simple observation like that can save you a ton of work.
So as you can see, this whole thing isn't just about randomly mixing chemicals and hoping for the best. No, it's about using a logical toolkit, a detective's framework to solve the puzzle.
And these are the golden rules you have to live by. First, always be systematic. Anions, then cations, group 0, then group 1, and so on. Second, trust your observations. The colors, the smells, any solids that suddenly appear, they're all clues. And maybe the most important rule of all, a negative result is not a failure, it's a success. It tells you what your salt isn't, which helps you zero in on what it is.
Okay, so let's bring it all home. Let's imagine we've run our mystery salt through this whole process. We've done our interrogations, we've raided the hideouts, and now we're ready for the big reveal.
So in our case, the gentle dilute acid test gave us nothing.
But when we brought out the concentrated acid, bam! We got that pungent, colorless gas, just like our clue sheet said, that points straight to our first culprit, chloride.
Then we moved on to the cation. The test for group 0 was negative, but as soon as we tested for group 1 by adding some dilute HCl, we got a thick white solid, a precipitate, immediately. Our roadmap points to only one suspect in that hideout. We've got him. It's lead.
And with both of our suspects identified, we just put them together. The positive cation, lead, and the negative anion, chloride. They combine to reveal the true identity of our mysterious white powder, lead chloride. Case closed.
You see, this whole approach, the systematic way of thinking, it's the foundation of so much of chemistry. It's a powerful way to turn a huge, complicated problem into a series of small, simple questions you can actually answer. So now that you have the detective's toolkit, what mystery are you going to solve next?